Hi, Professor Ackerman here. Today I want to go over an example of how to do a SolidWorks heat transfer simulation focused on radiation as the primary means of heat transfer. So I've got this example here of a vacuum former with an oven element, as well as a reflector, which is a flat aluminum sheet for simplicity here, and then the sheet of plastic, which is my target, what I'm trying to heat up. This example for vacuum former. So let's go ahead and take a look at what this looks like a bit more. I'm going to right click this and click change transparency just to show you what the heater looks like. So this heater I made is sort of like an oven element heater. It's got some kind of coils. It's got some heater block over here or power block that actually connects this to the aluminum plate, and also will have, say, power connections. I've got this aluminum sheet, which is transparent here. I'm just keeping a flat aluminum sheet for simplicity so I can get a pretty good reflection of this heat going straight up, straight down into the plastic and back to the heater. And then down here, I've got a plastic sheet that's going to be, let's say, polypropylene or PET or HDPE, something like that. Now, this is specific to a vacuum former, but the same constraints and what we go over here can apply to pretty much any radiation type simulation. Radiation is the primary means in a small system like this. So let's go ahead and start this. First, I'm going to change transparency back. We're going to go to simulation by making sure in SolidWorks add-ins, SolidWorks simulation is checked. It is, so we're going to go here. I'm going to click on new study. I'm going to look for thermal right down here. The default is static, but sometimes you have to go down here to advanced and click on thermal. Check. Cool. So we can see down here at the bottom left, I've got a thermal 1 study from before, and I just created a new thermal 2 study, right? So this is what we're going to be working with from scratch. Okay, now to start this, I'm just going to note one global contact that's bonded, and that's between this aluminum plate and the heater element, where I'm assuming it's basically screwed, or in this case, to simplify it, just bonded straight to the top of the heater block back there. And this is just floating in place based on the constraints that I have in the assembly. Okay, so we've got that. Let's go ahead and start adding our thermal loads. We right click on thermal load. First thing I'm going to do is add a heat power constraint. There's a couple other options here. We're going to work through heat radiation as well as convection, but first I want to add the heater power to show you what that looks like. So I click that. Now I could click on this entire block, so I can go down to the feature tree, go down to the heating element, click on that, and that would select the entire heating block, which can work sometimes. But in this case, really the heating elements are primarily these coils, not necessarily this block. So I'm just going to go and select all of the outside edges of these heating coils, or outside faces, I should say. I'm not trying to get the edges. Just select all the faces. And that's where the power is primarily coming from in this simulation, as far as radiation is concerned. Okay, so I've got all the different elements selected here. Looking good, nothing's left off. Nice. Okay, next thing I'm going to do, I have a lot of faces selected, so instead of per item, that would be adding a power for each face. I'm going to do total. I'm going to keep it at SI units. I'm just going to say I have a 500 watt heater. So we'll just start simple. It's kind of nice to have this option because we can then try different power settings to see how much power is required to heat up a surface for our application. So that looks good. Click check. Next up, I'm going to go back to thermal loads, right click. I'm going to add convection. Now, convection in this example is primarily going to be a means of having energy going out of the system because we're not going to have forced convection. I'm going to assume that this is just sitting in a room environment with just ambient room air. So I'm going to select all exposed faces to keep it simple, where there's going to be convection pretty much everywhere. I'm going to keep the units at SI. The convection coefficient I'm going to say is 10 watts per meter squared Kelvin. Without more information, it's kind of hard to know exactly what this should be. But in general, if you have relatively low airflow in your system, like in an ambient condition in a room, this should be somewhere in the 10 to 50 range, roughly. So I'm going to assume that the air is pretty stagnant, just sort of ambient temperature, not in a breeze, no forced convection with a fan. So this should be a relatively low number. If you had a fan or a breeze or just some source of air flowing, this would be much higher, and you might need to calculate this. But to just get something simple going, I'm going to assume there's a little bit of convection coefficient, a little bit of convection, and I'm going to say it's 10. The bulk ambient temperature is going to be 20 degrees C, so I got to add 20 to 273 for Kelvin to get the correct temperature in Celsius, so that would be 293 Kelvin for 20 degrees Celsius. Click check. Next up, we've got radiation. I'm going to right-click thermal loads again. I'm going to go down to radiation this time. So for the first one, I'm going to select surface to surface. Surface to ambient is a good condition if you have like a source of radiation that's relatively far from the rest of your environment, like the sun, for example. That's definitely surface to ambient, or just large gaps in between your system. It might make sense. But for this application, we do have surface to surface radiation primarily because this is a relatively small area, and I'm assuming most of the radiation is staying within the system. Okay, so surface to surface. For the heating coils, I'll start there. I'm going to select all the outside edges. That's where the radiation heat is coming from. Select all these. Okay. Now it is a good idea to keep your geometry relatively simple for a simulation like this, trying to be as accurate as you can, but not having too many faces if possible, just to speed up the simulation time. Okay, so we did that. Now open system versus closed system. If I click open system, I have this option to select the ambient temperature if you mouse over there. And this is definitely an example of an open system where I'm just gonna have 20 degrees C ambient. If I had a closed system, that would be like something in vacuum, or I could assume that there isn't radiation leaking out of the system. Then I would uncheck this and it would be closed. But for this application, this is sitting in air. And so this would definitely be an open system where there can be radiation to the ambient or around the parts. Down here, this is an important parameter called the emissivity. Now in the SolidWorks heat transfer simulation, they assume that everything is a gray body. That simplifies the emissivity and reflectivity and some other heat transfer complexities that can arise from radiation studies. So assuming it's a gray body, if I assume this is maybe ceramic, like a ceramic type heater, I can look up the properties for emissivity for a ceramic heater or steel heater or whatever application I'm using. For this one, I'm going to assume it's ceramic, and I'm just going to say it's a relatively high emissivity. If it was 1, that would be a perfect emitter. It wouldn't absorb anything, and it would just be straight up emitting radiation all around. So 0.9 is pretty high, so it's a pretty good emitter of radiation energy, thermal radiation. Okay, so that looks good. Let's click check. I'm going to go add the other 2 radiation sources, so radiation. I'm going to select surface to surface again. I'm going to click the bottom of this reflector. The reflector is made out of aluminum, and I chose aluminum here because it has a pretty low emissivity, and it's a very good reflector. So now I just used a flat plate here. In reality, if you're designing something like this, you might want a bit of a curve to this design, or at least wrap around the heating elements on the side to kind of trap more of that radiation energy and leaving less to rotate out the sides, and also sort of help direct the thermal radiation. But just to keep it simple, I'm going with just an 1/8" flat plate. So I'm going to do surface to surface. I'm going to select the bottom surface, which is primarily what's reflecting from the heater. It is an open system. I'm going to check the same ambient temperatures, 20 degrees C. And for emissivity, I'm going to make this 0.1 for aluminum. Now this can vary again depending on the material properties you're looking at. But if it's just standard aluminum, I think 0.1 would be a good starting point for emissivity, which means that it doesn't absorb a whole lot. It mostly reflects thermal radiation. Okay, check. Last one, radiation. And we're going to do surface to surface one more time. And I'm clicking on this top surface of the plastic sheet because that's primarily what's facing the radiation from the heater as well as the reflector up top. It is still an open system. It's still 20 degrees C ambient. And for the emissivity of this plastic, now this is something you may want to look up online to look up some properties of different types of plastics. But from looking up some different properties before I made this video, I saw that plastic's a pretty good absorber of radiation heat transfer or thermal radiation. And so I'm going to say this is maybe either 0.9 or 0.8 or something, or maybe I'll split the difference and say it's 0.85, which means it's going to absorb a decent amount of that thermal energy. But you might need to look up the emissivity for the material for your application. Okay, so we're going to click check. Awesome. I think that's pretty much everything. So we did heat power, we have convection, we got the 3 radiation from all the primary surfaces that are interacting. I think we are ready to try this. So one thing to note here is if you are getting confused by how many arrows and different indications or symbols I have here, that happens sometimes for complex models. Just right-click thermal loads, and then you can click hide all. And that just makes it a lot cleaner. You won't be able to see all the different boundary conditions and loads, but it just helps for viewing your results later on. If you want to get them back at any time, you just right click, go to show all, and you get them right back to make sure that everything is looking good. But for this purpose, I'm going to hide all so we can see the results a little bit more clearly. And now I'm going to go down here and click mesh and run. Now this may take some time. So it just meshed the simulation nicely. You may need to do mesh refinement if your simulation is more complex and there's more geometry, but worked pretty nicely here. So now the study is trying to solve for the different view factors here shortly, and just generally finish out the simulation. This may take a couple minutes. I'll let you know how long it's going to take, and I'll just kind of pause here in this live video and regroup when the simulation is done. Okay, it looks like our simulation just finished. It took just about 3.5 minutes. Now, that was on a relatively powerful computer I'm using here for this demonstration. It may take a little bit longer on your computer, depending on how your computer handles the SolidWorks simulation, but it shouldn't take too long for the steady state simulation. So hopefully we got results now that look good. So I do have some pretty rainbow colors as usual for kind of simulation SolidWorks, which is a good sign. I've got temperatures in Kelvin listed over here. We definitely see that the heater is quite hot. It's a little bit less hot towards this heater block. The aluminum looks pretty cool. And also the plastic looks like it absorbed a decent amount of heat. And it looks like it's got sort of a hot spot here in the center. So overall, it's looking like we got decent results. First thing I want to do is change the temperatures from Kelvin to something a little bit more typical. So I'm going to right click thermal, go to chart options, go to definition, or we could have clicked definition earlier. I'm going to change the temperature here as the output from Kelvin to Celsius. Click check. And now we've got our temperatures in Celsius over here. Looks like the lowest one is just above room temperature, about 27 degrees Celsius. Highest temperature is 410 Celsius. And that is this heating coil right here. So now it looks like this, based on the turquoise, is somewhere around 140-ish degrees Celsius. If we want to take a look in more detail at the temperature distributions for this particular simulation, what I can do is right-click thermal. I can go down to probe, and I can actually probe specific elements like the middle of this sheet. It'll identify whichever node. There's just a bunch of triangles in the mesh, and it'll pick one of the nodes of those triangle meshes. I'll click the edge over here to see how much it decreases towards the edge. I'm going to click the middle of this aluminum plate just to see how much cooler that is. And I'm also going to click where the heater is the hottest, just to get a little bit of perspective of how hot it is relative to the rest of the system. Okay, so we've got the values down here. We can export this into Excel or MATLAB or whatever we want to use. Just copy these values. Or you can just quickly look at the plot right here, which I like to do. Just take a look. So this first point is in the center of the plastic sheet. It looks like we're getting just about 165 Fahrenheit right in the middle of that sheet, which is pretty good. That's actually going to be a softening temperature for a lot of different plastics, and even close to the melting temperature for some. So for vacuum forming, this seems pretty good. Down here at the edge, it's a little bit cooler at around 100 degrees C. So we may need to think about how do we orient the heater, or how do we adjust the reflector, or how close we put the plastic, or just the parameters we put in, like the power of the heater, if we need to think about how we can get a better temperature distribution. But it does look like I've achieved a pretty decent target with these parameters. Looks like my plot disappeared down here. There we go, brought it back up. And then down here, this is the aluminum reflector. So that's just about 40 degrees C, maybe 50 degrees C. So way cooler than the plastic because it mostly reflects rather than absorbs the thermal radiation. And we see that the heater is quite hot, definitely the hottest part of the system. Got to be careful with that. And that's still about 400 degrees Celsius. So pretty good results for a vacuum former application. And we could then tweak the results to see how these different parameters are going to affect it. Like maybe I have more or less convection. Definitely if I have a different kind of heater, more or less powerful. And even these radiation variables, like especially the emissivity parameter, if we have better data of the material properties, these can all help us refine this simulation. So hopefully that gives you an idea of how to use a SolidWorks thermal radiation study for just a simple steady state example. And you can use this for design purposes. I do want to go over one additional aspect here. you can actually do a thermal transient study, which can be pretty powerful to see how long it's going to take to achieve this steady state configuration. If I wanted to do that, all I have to do is go up to thermal. I can go to properties and I can change it from steady state right here to transient. I'm going to look at, I don't know, 10 minutes. So let's do 10 minutes, 600 seconds. The time increment can be relatively large just to speed up the simulation. So I'm going to look at it every minute. So there should be 10 total time steps here. I'm going to leave all the rest of the parameters the same. Click OK. Now when I do a transient study, it's going to do a bunch of these studies again at different time steps. It's going to take quite a while. So just as a warning, this can take a long time for your simulation. But just showing you how to set this up, and I'll even show you the results at the end when it's done running. You do have to set up a thermal load of temperature. You've got to set the initial temperature. So I'm going to set the initial temperature up here. This option only appears for the temperature if you have the transient selected for your overall simulation. For the elements here, I'm just going to select the entire bodies. So when you select the entire part, you will then be able to say this entire part is at room temperature to start with. Otherwise, if you click on the surfaces, it'll assume the inside of that part is absolute 0 or negative 273 Kelvin, which will throw your results off quite a bit. So you want to do something like this. Okay, cool. So we've got our initial temperature, and now we can go ahead and run our thermal simulation, our transient thermal simulation. If I right-click Mesh and Run. Now this is going to take quite a while because it's going to mesh it. It's then going to do 10 different time steps, each of which takes a decent amount of time, a couple minutes. So I can take a look at this, keep an eye on it, probably come back after I'm doing something else because this can take quite a while, so as a warning. But if you want to see how this thermal study is going to proceed over time, this could be a really powerful option when you're doing a radiation study. So I'll come back when the results are done, tell you how long it took, and we'll just take a look. All right, so we just finished our transient thermal study. It is now just over 30 minutes later. So as I said, it does take quite a while. Really, I did 10 time steps, so it took almost right on 10 times as long as the one thermal radiation steady state study. So if we wanted to decrease that simulation time, we could either decrease the overall simulation time or more effectively, I'd say, we could have fewer time steps. So we would only have to run the simulation maybe 5 times. We checked every 2 minutes. You can have a pretty big time step in a thermal study and still get pretty good results. But let's take a look at what we got. So after this 30-minute transient thermal study, you can see the temperature Celsius down here. Now, right off the bat, this heater is getting pretty hot. Looks like right around 96 or just under 100 Celsius. So that's right on the first time step. So that heats up very quickly because of that 500 watt power source. I can click forward in time right here. Right, so we see the colors starting to change as I click forward in time. And we can see the values, the max value has also been changing while I've been clicking. Another tip is you can actually go backward in time. Oop, don't double click on that. Just steady single clicks. Now time step 1, I can go back to time step 10 in reverse. So I can jump between time step 1 and time step 10. And here it looks like we're just at about where our steady state thermal study was predicting. Maybe a little bit below that in about 10 minutes, but pretty close. So reasonably similar results overall. What I can do also is now look at how the temperatures change over time. So this is why it's really powerful, I think, to be able to do a transient thermal study. I can right-click Thermal, go down to Probe. Right, I'm going to again probe pretty much the same spot. So I'm going to probe right in the middle. I'm going to probe at the outside edge. I'm going to probe the top middle of the aluminum plate just to see how hot that gets. And I'm also going to probe the hottest part of our heating element, there-ish. So I've got 4 nodes. Now you'll notice down here at the bottom left, I now have this response option with a little clock symbol. Before I just clicked on plot, which is totally fine. There were other options here as well. But on the transient study, the response plot is available. Clicking on that pulls this up, which is pretty cool. Make this a little bit bigger. Okay, so we can see the temperature of the heating element right here get pretty hot, approaching, excuse me, approaching where it almost achieved on the steady state simulation. And then this is the middle of the plastic right here. You can check the nodes down there to see where we're at. It looks like in about 10 minutes, it got to 120 degrees Celsius. So it looks like that steady state point is a little bit further beyond that, maybe at 15 minutes or so, or even a little more. The outside edge is a little bit below 100 now. I'm at 80. And then the aluminum plate has gone up to 34. So we can see that to achieve the steady state simulation results I got before, it's going to take probably a little bit more than 10 minutes with these parameters in this simulation. So again, all these different results are affected by, I click check, they're affected by how much power I'm putting in, the overall geometric considerations of your system, how you're designing that. Are you letting some of this thermal radiation escape out the sides, for example? Maybe I need to think about that reflector design. And just generally the configuration of the heater and how that heat is distributed, reflected in the system. The convection coefficient may be a little bit high for application, hard to know. This is just a standard one I like to pick for ambient configuration. The emissivity of each of these parameters we can maybe adjust depending on what data we have about it. And yeah, those are the main parameters that we can adjust. But yeah, hopefully that gives you a good insight into how you can conduct a thermal simulation, both from a steady state perspective as well as from a transient perspective. Another thing I like to see on this transient perspective that's kind of cool is you can create an animation here, so you can see how that changes over time. You can also save it as a .avi file, which is kind of neat. But yeah, hopefully that gives you a good starter guide on how to do radiation analysis in SolidWorks. And good luck with your analyses, and hope this helps.